Welcome back to ECE 442-542. Oh, maybe you're okay in the class. They're working on a quiz, actually, which is how we wanted to start today's class. I will now switch over to the class, hopefully, to where they can see what I want to announce while they're still maybe formulating an answer to the quiz. Homework number 6 is due on Monday. Office hours this Friday, I have all sorts of activities going on, so I'm unable to make that time. If you were hoping to see me, send me an email and we can try to set something up. I don't know when it would be, because right now I'm blocked from 8 to 5, essentially, on that day, running all over. So you'll probably see me, but I'm unavailable, whatever that means. There is review material for exam number 3 on D2L. If you have questions or if you want particular topics discussed in the review session, there's a quiz on D2L, and we will have a review session the next time we meet after that lecture, which will be on the 9th of April, and our exam is a week from today, exam number 3. Hopefully that doesn't catch you too off guard. Today what I want to do is really get into root loci, and I'm starting by trying to get you comfortable with really some of the ideas or concepts that we are going to be talking about in the root locus, and that was via a quiz. And then we'll look at some example diagrams. We will numerically compute some roots, closed loop poles, and that will actually be marching through the root loci. And then we'll talk about generalizing the notation, and we'll get into sketching rules of the root loci. The root locus diagrams are all based on this generic structure, on this fixed structure for the closed loop system. There's negative unity output feedback. We have the single gain parameter K extracted from maybe the compensator and the plant. That's why I'm labeling it as G bar. That G bar could contain the plant G of Z and pieces of the controller capital C of Z. And the piece of the controller that we're actually isolating on is K, and that allows us now to write the closed loop transfer function between R and Y as this kg bar over 1 plus kg bar. Where again, G bar is not necessarily the G. It could contain some of the pole and zero factors from the controller. That's why I'm labeling it as G bar. But we should be comfortable now finding that closed loop transfer function, and once we have that closed loop transfer function, we know the dynamics of that system are now governed by 1 plus k G bar of Z, or the values of Z that cause that to vanish. Those are the poles in our closed loop transfer function, and they actually govern the dynamics of that closed loop system. And I'm going to keep telling you where these rules come from for sketching the root loci, and essentially it all comes from that denominator expression. 1 plus kg bar, if we set that equal to 0, we can solve that for kg bar. That means kg bar, if it's a point on the root locus, we have this z-plane, and the root locus is going to be some branches that are sketched on that z-plane. If a point on the z-plane belongs to the root locus, it has to satisfy kg bar equaling -1. And -1 we will actually separate into two pieces. We'll have the magnitude piece. The magnitude has to be 1, and the angle piece, or the phase piece, is this -180. Those are our two conditions that really all of the root locus diagrams are sketched based on those underlying conditions. And here's how we started today. A little bit delayed. Hopefully we'll still be okay with the hiccup that we experienced earlier. But here was the quiz. I hope I wrote it down accurately enough because I was doing it from memory. It was on the tablet but not anywhere else until I wrote it on the Elmo. So now it's on the Elmo, which you don't need to know. But anyway, here is our G-bar. And how did you solve that question? I know some of you immediately pulled out your calculator, and I just had to take a deep breath, do some relaxation techniques so that I didn't go over the top. But I want us to start thinking about this maybe graphically so that you visually have some intuition as to how do I find the angle of that transfer function for any point in the complex z-plane. That's the idea. Now you can solve it many different ways, but I was hoping that maybe you would do more than just, you could plug in that complex number, right, for z. And then g bar of z will be a complex number, and you just find its angle. That's fine, but I want us to start thinking maybe with diagrams. And in particular, we can now think about the z-plane. And once we have the z-plane, now we have the real line, or the real component of z, and the imaginary component of z. And what I'm hoping you might start doing is plotting immediately the poles and zeros on that z-plane. That'll give you some points on the exam. But here we have no finite zeros, so you will not see any open circles. But we have two poles. The first pole is at the origin, or one of the poles is at the origin. I didn't want to say one because one of our poles is at 1. We have a pole at 1 and a pole at the origin. And what I was asking you to do was actually find what is the angle of g of z at that triangle. And the way to do it with the transfer function graphically is to say, oh, let me find the angle from each of these factors to that triangle and add them up. And if I had 0 factors, I would find the angles from that 0 to the triangle, add those up, and then subtract all of my pole angles because the poles are in the denominator of that expression. And you know how to compute with polar numbers if you have a ratio. If you had some polar number over another polar number, you would subtract the angles from the denominator of those from the numerator. What am I saying? I'm saying first, I would get out your drawing equipment and, in fact, start drawing a line segment to that triangle from each of your poles and zeros. And then, since we're interested in the phase, we measure this phase relative to the positive real axis. And what did I label this? Let me label this angle theta P1, since that's associated with the pole at 1, and let me call this angle theta P sub 0. Those are the only two angles that I have associated with that transfer function, because I only have the two factors that are actually pole factors. If I had a 0, let me just hypothetically say that I had some 0, which I really don't want to do, but I will. Let's say that we now had a 0 there, so that it was now over here. then we would go from there, and I would label that theta sub z. Are we clear on how to basically construct or create these angles associated with the singularities, the poles and the zeros? And once we have those, now if we wanted to compute the phase of that, we would have all of our zero angles. We would have this theta of z in this case minus all of the angles from our pole. And now we now need to determine what those angles are. And if you've sketched your diagram, your z-plane, with the same dimensions on the real line as the imaginary axis, the angles will actually be correct. So you can visually inspect or sort of intuitively have an idea what angle you should be expecting for if you calculated the angle. In this case, we do not have a theta of z, so I'm going to, do I dare erase it now? No. So I'm going to leave it on there, but it's not there. Is that okay? So now the angle, what is the angle theta p sub 0? Now this is why you took trigonometry in middle school or wherever you had trig. Maybe elementary school now? I don't know. I had it when I was a grad student. No, I'm just teasing. But now we have trigonometry, and the angle is what? I go up a half and I go over a half. So that's the inverse tangent of 1/2 over 1/2. It's 45 degrees, and you can visually see that if it's drawn accurately. So this angle right here is 45 degrees. The other angle, theta p1, I like to work with acute angles. And so now I'm saying, oh, theta p1 is 180 degrees minus, and this was cooked up special so that I could easily find these angles, but that's also 45 degrees. So I have 180 minus 45, or theta p1, since I'm measuring it with respect to the positive real line, is 135 degrees. So that the angle of g bar of z at z equal to 1/2 plus j 1/2 is now minus the sum of 45 and 135, or minus 180 degrees. So in fact, that triangle would be on the root locus diagram that we would sketch for this g bar of z. But we'll get to that in a minute. Are there questions on how we graphically found? Have you done this before? You really should have done it in 320. If you had my 320, hopefully you would do this with sketching these angles. And I just like drawing X's and triangles, etc. But you could have worked this many different ways. If you have a calculator, it's pretty easy, depending on the kind of calculator. But you could have just said, oh, the angle of g bar of z is 1 over z, z minus 1, with z equal to, and some of the calculators allow you to do that. You have that vertical bar, that width, and you can do it. Yes? Now, I'm not quite sure what you're asking, actually. Say your question again. Why am I having a hard time with your question? No, say it again. So you calculated, okay, so now what you have calculated, you did what I just did, right? You evaluated g bar of z at z equal to 1/2 plus j 1/2. You can substitute in that, and then you can evaluate that. You came up with g bar of z as a complex number. Well, maybe it didn't have an imaginary part, but it's still a complex number. You ended up with the angle of -2. Is that what everybody calculated, or did you, when you evaluated it, did you get -2? Is that what I came up with? I think it was. So now you have the angle of -2. That's now what? Well, that's the angle of 2 at an angle of -180 degrees, right? -2 is over here in the z-plane, and we're getting there going this way to give us the -180 degrees. So it's 2 units from the origin, and you could have said, well, it's also this, and it is. It's 2 at 180 degrees, or it's 2 at -180 degrees. We're just establishing the convention that we're using the negative angle. It's the same number. I don't know if that even answers your question. I'm sorry that I didn't know what you were asking, but you were simply evaluating g of z at the location, and that's fine. Now I'm wanting us to try to get comfortable doing it in diagram form, because that's what we're drawing when we're drawing the root locus. Are there other questions on this? Yes. If what? If we ended up evaluating and that complex number ended up being 2, now we want the angle of 2. So what I would do, if it's not making any sense, I would sketch my z-plane and plot 2 on the z-plane, and now I would go from the origin and measure what angle do I have from the origin to 2, and it's 0 degrees. Is that clear? So just stand at the origin and start rotating around. Get up and do it if you need to. On the exam, if you start getting up and twirling around, I'll go, uh-oh, but I'll probably be okay. Sometimes we have to do something physical. That's why I'm moving around. I can sometimes think better when I'm moving. If I'm stuck at a desk, sometimes I get hung up and I can't understand questions. So I have to move around. Other questions? But we now need to be thinking about complex numbers graphically as far as their polar form, length and angle. And we're measuring those angles with respect to the positive real line. All right. So let's look at some examples. Boy. Can you guys have young eyes, you can see those, right? And you'll have access to this, so you don't have to sketch them. I'm really wanting you to start developing some feel for what these diagrams might be. Here is a g bar of z. How many poles are there in g bar of z on the left-hand side? 1. And where is it located? At 2, and that's where I've indicated the blue X. And if I have 1 pole, how many branches of the root locus am I going to have? 1. I'm going to have as many branches of the root locus as I have poles. And where do I have the red line is indicating the root locus. And all the points on the root locus, all the points on the red line have to what? They have to satisfy those 2 conditions, a magnitude condition, which we'll worry about that in a minute, but the phase is the important one for now. And what's that say? Every point on that red line has to have an angle of -180 degrees, and this is with our convention. It has an angle of 180 also, but we're going to just say we'll call that -180 so that we have the same answers. And you can see that if you look anywhere to the left of that blue X, in that particular G bar of Z, all of those points have an angle of minus 180. What about the G bar of Z on the right? How many poles do we have? 2, and they're at 0 and 2. And how many branches of the root locus do we have? 2. Here's where you get confused sometimes, is the fact that we have one line segment between 0 and 2 that actually possesses 2 branches. It contains 2 branches. One branch, we're going to learn, the branches start at the X's and they end at the O's, at the circles. And if we don't have any finite zeros, we're going off to infinity. And in this case, if we go off to infinity, if we have 2 branches going off to infinity, they're going off at plus and minus 90 degrees. They may bend around before they get to plus and minus 90, but asymptotically they're going to approach plus and minus 90. In this case, because we have 2 poles and only 2 poles, nothing else, they are going to meet exactly in the middle and go up and down. So those 2 sketches for the root locus you should have in your hip pocket or on your crib sheet or instantly on the exam in a week. Now we get a little bit more interesting, and we'll talk about these more, but I'm just wanting you to see that there's more to a root locus than straight lines. The one now on the left, it's just pretty, isn't it? How many poles do we have? 2. Do we have any finite zeros? We have 1. And where is it? It's actually at the origin. And in fact, when we have 2 poles to the right of 1, 0, the root locus is actually going to be a circle. And the center of that circle is right at the 0. And the radius of that circle is the geometric mean of the distance between the 0 and the first pole times the 0 and the second pole. In this case, the geometric mean is 1 minus 0 times 2 minus 0 square rooted. It's the square root of 2. And the radius then is the square root of 2 from that 0, which is at the origin. And so now you would just get out your drawing instrument, which is could be a protractor, it could be a compass if you were allowed to have sharp objects. So you now have a compass and you set that radius to 1.414 and draw a circle. And you then know that you're breaking away. That's one of the terminologies that we're going to be using. So we have a breakaway, z sub b, at a square root of 2 distance away from the origin. And we'll figure out where this is coming from. Right now, I'm giving you sort of one little trick. When you have 2 poles to the right of 1, 0, you can always use this strategy. Then it's obviously coming back in. You have 2 branches of your root locus. What's the pole 0 excess in this problem? 1. So the pole 0 excess actually tells you how many branches of the root locus are going off to infinity. You have a pole 0 excess of 1, and you have 1 branch going off to infinity. And when you have 1 branch going off to infinity, it's going off to minus infinity. Up above, let me go back and see if that strategy still holds. What's our pole 0 excess on the right? It's 2. So how many branches do you have going off to infinity? 2. And they're actually splitting 180 degrees, or the fundamental angle right here is 180 divided by that pole 0 excess, or 180 divided by 2, or 90 degrees, and they have to uniformly split this 360 degrees. So you know that one's going up at 90 and the other one's going down at 90, because they are equally dividing the z plane. The branch of the root locus is the vertical line up and the vertical line down. It's also, well, this is one branch and this is another. No, so we have four pieces, but actually two branches. We always have the number of branches that we have poles. And so now let's say we start at 2, one of the branches goes to 1, it's going to go halfway between the other pole and it was at the origin, so we know our breakaway here is at 1. And it doesn't matter if it goes up or down, it just takes one of the paths. So 2 goes up, 0 goes to the right and goes down. And those are your two branches for that root locus diagram. The re-entry point is at minus 1.414 now in the lower left. And when they come together, they can't stay together. For some reason, they just can't stay together. But these branches then, one goes to the 0 and one goes to infinity. Because we had one branch going off to infinity, we had a pole 0 excess of 1. And we said that the branches start on the poles and end on the zeros, the finite zeros and infinite zeros. But in the finite z-plane, the branches are going to go to the zeros, and then the others are going off to infinity, the zeros at infinity. What's happening in the lower right? Well, you should immediately be able to write down x's and o's on your diagram, on your z-plane. You should be able to factor the denominator, factor the numerator, and immediately put in the x's and the o's. We have a pole at minus 1/2, we have a pole at 1, and we have a pole at 2. We have a 0 at the origin. How many root locus branches do we have? The other way I could have asked that question is how many poles are there? 3. So we have 3 branches, 3 poles. I hope. I better look, huh? So now we have 3 branches of the root locus. They each start at a pole. And how do we know that there's a branch between, or 2 branches actually, between 1 and 2? How can we check that that's a part of the root locus? How do we do this check quickly? How can we quickly check? We'll basically state a quick rule in a minute, but it has to satisfy one of those 2 conditions, and it's the phase angle condition. So now you just walk to a point between 1 and 2, and you say, if I'm right here, let's say 1 3/4, all of these poles and zeros, their angles have to sum to minus 180 if I'm on the root locus. And the only angle that's other than 0 at 1 3/4 is the angle due to the pole at 2. And it's 180 degrees. The others are 0. So we have 0 minus 0 minus 0 minus 180. Or a minus 180. The same with, why did I know that there was a branch between the pole at minus 1/2 and the origin? Well, I better have all of the poles and zeros angles eventually summing to minus 180. The angle of this pole at minus 1/2 to the origin is what? What's its angle? What's the angle from the pole at minus 1/2 to the origin? 0. What's the angle from the 0 at the origin to minus 1/4? So now you stand at the origin and you go, okay, I need to go all the way over there. I didn't do my yoga this morning, so I'm trying to. So you can get up and start doing this and convincing yourself. So that 0 contributes 180 degrees. Each of these poles to the right, the 1 and the 2, they each contribute 180 degrees. So I have 180 degrees minus a total of 180 plus 180. So two of those 180s cancel, and I'm left with minus 180 for all points between minus 1/2 and 0. And that's how I know how to immediately shade those segments on the real line. And what's the quick way to do that? You move, here's how I like to describe it. Anybody like bread? So now we have this long slice of bread, not slice, a long loaf of bread, French bread, let's say. And it's the length of the real line, the real axis. We now want to cut it everywhere we have a pole or 0. That gives me certain segments. In this case, I would have how many pieces of French bread? I would have a piece to the right of 2, a piece between 1 and 2, a piece between 0 and 1, a piece between minus 1/2 and 0, and another piece between minus 1/2. Did I count 5 pieces? So I have 5 line segments. 1, 2, 3, 4, 5. And now I could ask you, which of those 5 line segments belong to the root locus? How many real line segments belong to the line, how many of those 5 segments belong to the root locus? 2, we can see that. But how do you find those 2? Well, you go to those and you say, do I have poles and zeros, an odd number of poles and zeros to the right of my location? If I'm at 3 and I look to the right, do I see any poles and zeros? No, so that's not a part of the root locus. I step back and I step between, let's say, 1 and 2. I'm at now 1 3/4, and I say, do I have an odd number of poles and zeros to the right of me? Yeah, I just have the guy at 2. That's odd. So that segment is a part of the root locus. And there's actually 2 branches of the root locus on that one line segment. Is that clear? So I make a distinction between the line segment and how many branches. What about at 3/4? Now I stand at 3/4 and I look to my right and I count the numbers of poles and zeros. I see 1, 2. 2 is even. Isn't this tough? And the reason that works is because of they each are contributing 180 degrees, and if you have 2 of them, or an even number, you're going to be at 0 or 360. If you have an odd, it's going to give you eventually a minus 180. That's how that works. Now you can see that quickly how to shade the real line segments that belong to the root locus. Oh, what else have I need? We have how many branches in the lower right? How many root locus branches? How many root locus branches do I have on the far right, lower right? 3. I have 3 poles. I have 3 branches. How many poles what's my pole 0 excess? 2. So how many branches of that root locus are going off to infinity? 2. You just have to keep that number on your hand, and now you know how many branches are going off to infinity. And we'll learn where those are going later. Yes? No, the line doesn't need to be, so the question was a good question. Right above, it was straight, wasn't it? As soon as we went off the real line, it was, my drawings are terrible, I apologize, but those are actually going perpendicular, plus and minus 90. Down below, the reason it is not going straight up and down is because I have more than just 2 poles on my plane. I have a pole and a 0, and they impact, they bend things a little bit. So now my root locus curves a little, but they're going to be kind of nice curves because every point on the root locus has to what? Sum to minus 180 as far as an angle. So they're going to be smooth curves, but they will eventually bend to what we will call asymptotes, and we'll learn how to sketch those asymptotes and where the centroid of that asymptote is. But we may not get there until after the exam. That's okay. The next one, lower left. Apologize for being a little busy. But you can immediately write down the X's and the O's. And now you can immediately identify the line segments that belong to the root locus. How many line segments do you have? Total. Think about your bread. Get out your knife and cut your bread. How many sections of bread do you have? Total. How many total sections of bread do you have? 4. How many of those sections are a part of the root locus? 2. Not all 4 are on the root locus, are they? And did I draw this right? If I stand at 1, how many poles and zeros are to my right? 1, and that 1 is odd, so I know that that particular line segment belongs to the root locus. At the origin, I have 2 poles and zeros to my right, so that that line segment is not on the root locus. I go to the left of -1/2, any point there, and I have 3 poles and zeros to the right, so everything there is a part of the root locus. What's my pole zero excess? 1. So how many branches do I have going off to infinity? You see why your fingers are important? There's your memory. You don't even have to think if you want to use your fingers. And we won't even have you having to take off your shoes because we probably won't have that many branches. Probably won't have more than 10 on the exam. So you can keep track on your 2 hands. Lower right, pole zero excess. But now do you see the way that these branches are directed? Those are the arrows. We start at the poles, the open loop poles, and we end on the open loop zeros. And we also end at the zeros at infinity. What determines the shape of the root locus? Well, you already know the answer to that. It's the 2 conditions, but we'll sort of go there a different way now. Here's our example number 2 that we've played with before. Let me expand this a little. Here is our generic block diagram in root locus form. We've isolated the K. We can find the closed loop transfer function. That's Kg over 1 plus Kg. We have a ratio of ratios, and we can get a common denominator in both, and that common denominator cancels, and now we're left with K over Z times Z minus 3/2 plus K. Closed loop poles are governed by that denominator, 1 plus Kg of Z, when that's equal to 0. But if you look at what happens, it's really the numerator when you get that all over a common denominator. The 1 plus Kg of Z, the 1, you have to essentially put that in a rational form so that you get a common denominator, and now the numerator, when that's equal to 0, of 1 plus Kg of Z, that's what governs the poles of your closed loop transfer function. So if I talk about the numerator of the denominator, you know what I'm talking about. Maybe. It sounds a little weird, but the numerator of 1 plus Kg of Z is really the denominator of your closed loop transfer function. And that's what we're looking for those values of Z that cause that to vanish. And those are your closed loop poles. So we want to know, as I adjust K, that's my gain, that's a knob, you can think of that as a knob. I'm turning that knob from 0 to infinity. And as I turn that, I want to find out what the values of Z are that cause that to vanish. So do you see I have an infinite number of roots to this second order equation? It all depends on the value of K. Whatever I pick for K is going to influence the values of Z that cause that to vanish. So my poles of my closed loop system are obviously influenced by that gain of my controller. However I set that gain is going to influence the roots of that denominator polynomial. That's why control is really adjusting that knob. So let's just evaluate that expression for some particular values of K. If I plug in K equal to 0, it's maybe easier to see in this blue line. If I set K equal to 0, now it's already factored. I have Z times Z minus 3/2. I have a 0 at 0, a 0 of that polynomial, which is a pole, at 0, and another pole at 3/2. If I plug in a K of 1/4, and here's where your calculator can come into play. You can plug in these values, and in fact, these two columns of Z's, those are the red dots that you're putting on your Z plane, and now you just connect those red dots and you've drawn your root locus. If you wanted to do it without any thought, if you just wanted to do it computationally, you just sit there and start finding the roots of this polynomial for different values of K. That's another way of thinking about the root locus. So let's draw the root locus based on this. I simply stepped through some particular values of K and evaluated that quadratic and found the roots of that quadratic. Is it clear what that table represents? That's just solving a quadratic for different values of K. And all the K's between those are a part of the root locus. Let's say that I now call this the squares. So now I have a square at basically 0.2. I'm not going to be able to get much finer than that. And where are my poles? Actually, my open loop poles, I have one there and one there at 3/2. One of my poles, when I crank up the gain to 1/4, which I'm representing as a square or a box, is going to be at roughly 0.2, and the other one's going to be at 1.3. So do you see that they're not moving at the same sort of rate towards the other? One went 0.19 and the other one went 0.19. But they don't necessarily go at the same rate. One can zip further than the other one, depending on the location. But here I have two poles and only two poles, and that's why they're going to come together at the same value. Where are they going to meet in between these? Right in the middle. So all you have to do is know how to divide 3/2, and we know that they better meet at 3/2 divided by 2 or 3/4, and that's where they're going to go up and down at 90 degrees. And that's what we're seeing here. Let's say that I now crank up the gain to 1/2. Now I've moved to 1/2 and 1. So is it clear what I'm doing? I have boxes, then I have triangles. What happens next? Let's say that I now have a triangle down at 9/16. Now I'm right at 3/4, and I have two triangles on top of each other. I crank it up to 3/4, and now I am right there. Whoops. Wake me up. Somewhere there, right? That should be on the vertical lines with a real part away from the origin of 0.75. And at 1, a gain of 1, oh, I've run out of symbols. What's another symbol that's unique? A star, okay. So now I have a star, and that's actually right on the unit circle in this particular collection of numbers, of a pole at the origin and a pole at 3/2. And now we've computationally drawn the root locus. We have a branch going here, another branch going there, and one goes up and one goes down. And in fact, what's the range of stability for this system in a closed loop configuration, K? Now, hopefully from this data, you can determine what K needs to be stable. K needs to be bigger than. When did we first become stable? Or where were we at? We should have at some point been on the stability boundary. As we cranked K up from 0 up to, where did we finally get on the boundary of stability? For what value of K? When we had a pole at 1/2 and another pole right at the unit circle at 1. We cranked up the gain K, and those two poles are going towards each other, and the unstable pole now we are stabilizing by increasing the gain K. K now for stability needs to be bigger than 1/2 and less than, if I gave you this chart on an exam and said, here's G bar of Z, and I say, what's the value of gain, or what's the range of K for stability? Could you put down the right answer? Or do you know how to find the answer? I apologize if this is a little small, but you can read this later. But this is now how you could do this with a TI calculator. You could just say, oh, here's my polynomial, and now you can just jump up and copy this down and say, oh, let me replace this K. I started at 0.25. Oh, let me go up and now say with K equal to 0.5, with K equal to 9/16. I did that because it's right at the breakaway point. And then another one is at K equal to 3/4. And did I do the other one? Then with K equal to 1, it gets me right at the unit circle. All of these different ways to try to help you see or convince you of what this root locus represents. Here's our generalized notation that we're going to assume exists in this class. Suppose somebody has a controller that's a ratio of polynomials, zero factors and pole factors, and we have a plant or a system, G, that also has pole and zero factors. To start talking about a root locus, we want to isolate the gain K, which means that we are going to lump all the pieces of C that aren't K in with the G and call that mess G bar. And I might say, oh, I have a numerator polynomial and a denominator polynomial for G bar. What's the root locus for that system? Can we sketch it? The zero at the origin and the pole at the origin, those are stable. That's okay. We can cancel those. So help me sketch this. Here's my z-plane. I want to sketch this root locus. What's the first thing I do to sketch the root locus? I probably plot the poles and the zeros, finite zeros. I have a pole where? I have a pole at -1 and a pole at 2. Do you immediately know which part of your French bread that you've sliced up belongs to the root locus? How many sections of that bread do you have? Total sections. 3. How many of those sections belong to the root locus? 1. And that section includes 3, the origin, or -2? Is that question clear? I have 3 segments. One of those 3 belongs to the root locus, and now I just picked a point in those 3 segments. I said one of the points in the rightmost segment was 3. Is that on the root locus? The other point I picked was the origin. That's on the segment between -1 and 2. Is that on the root locus? And now you know that I can't go back and forth, but I really would like to just emphasize that and say, there's my root locus. This one is going there, this one's going there, and I don't have a branch to the left of -1. Now, these two are coming together. Do they just eternally stay on the real line? What's my pole zero excess? 2. That means what? I have 2 branches at infinity. And in this case, because of this simple configuration, we know exactly what those 2 branches are doing and where they're doing it. Where are they breaking away? Halfway between those. And now I have -1 and 2, so I can split 3 to give me 1.5, and now I just go 1.5 to the left of 2 or 1.5 to the right of -1. So now I'm at 1/2, and there's where I'm at. Now, on this, can you tell me anything about stability of K? What values of K would result in a stable system, closed loop system? Suppose I now said, well, let me sketch the unit circle, and then I'll be able to think through what's going on. There's my unit circle. Does that help guide you in determining, is there a range of K that would be stable? And if you run out of time on an exam, I would just start drawing pictures. What do you know? You know the lower limit is where for K? Is it 0? With k equal to 0, is my system stable? K equal to 0 means open loop. In the open loop, is that system stable? No, because I have a pole at 2, don't I? And at -1, which is right on the stability boundary. That's not really favorable either. But it's better than 2, isn't it? So I'm not stable at k equal to 0. I have to crank up the gain some. And which of these locations on the root locus determine the lower limit of k? Do you see how what I'm trying to push you into thinking? As I crank up k, this branch goes there. This branch goes there. The blue branch, if you can see that, as I crank up the k, has it changed from unstable to stable? No, it's just stable, isn't it? Once you get off of 0, k is okay with that one. But what about the yellow? I have to crank that up enough to what? I need to get to at least that location before I become stable. So now you would evaluate k, g bar of z, at z equal to 1 and solve for k. Because you know the magnitude of that has to equal 1. So if we now had, kind of getting ahead of myself, but here we have k, g bar of z equaling 1. That's our magnitude condition. We know that's true on the root locus. We could solve this for k. We now have k over z plus 1, z minus 2 equaling 1, taking the absolute value of all of these pieces and assuming k is non-negative. I solve this for k, and now I could evaluate that at z equal to 1. If z is equal to 1, what ends up being my value for k? I have 1 plus 1, there's 2, times 1 minus 1, which has a magnitude of 1. Where was I? 2 times 1? Is that right? What's my lower limit for stability? 2. This is, let's say, k box. That is when k equal to z plus 1, z minus 2, evaluated at z equal to 1. That ends up being 2. But if you ran out of time on the exam, you could say, oh, k lives between k sub box, and draw me a box and show me that, oh, there's where the lower limit is. And now I say, oh, I'm really out of time, but I know k triangle. What's k triangle? That's this. But where is that on the root locus? Where's the triangle? Do you see what I'm trying to ask? It's where the vertical lines cross the unit circle. It's right at the intersection of the unit circle and the branches of the root locus that are going outside the unit circle. You can't crank k up bigger than that without going unstable. Here is my triangle. And the k that gets you there gets you to the same point downstairs. So you just have to calculate it at one of those values. And I will just share with you, but that actually is 3. So for stability, and do we know what part of that, so this z triangle is what? What are the coordinates of that? 1/2, right? Plus J, I don't know, Y. Y, okay, fine. But what do you know the magnitude of Z delta or Z triangle is? What's the magnitude of Z triangle? Where is it? It's on the unit circle. So you know that unit circle has a distance of 1 from the origin. Z triangle has a magnitude of 1. You can now take the magnitude of Z delta equal to 1 and solve for Y. There's only one unknown in that formula. Now you know what Z triangle is. You can now find that Z triangle, plug it into your K expression, and end up finding that K is equal to 3. Do you follow that logic? And did I do that? Y actually ends up being the square root of 3 over 2. Hopefully. Check my math. Okay? This should not come as a surprise to you. What is 1 plus kg bar of z? Where is that? Where did that come from? And the answer is, Alex, the denominator of the closed loop transfer function. Right? That's 1 plus kg bar of z. There's nothing funny about that. Well, maybe there is. That's okay. Humor helps you learn. Did you know that? Maybe. All right. So we've now found that 1 plus kg bar of z is what we're interested in. That's the denominator of our closed loop transfer function. And from that, we get these two conditions. And the root locus is based on those two conditions. The phase angle condition, and now you know exactly what segments of the real axis belong to the root locus. That should be a given on the exam in a week. If you don't learn anything more, don't forget that. Okay? That'll at least give you a couple points. Maybe more, depending on how generous I am or feeling. But now if I said, okay, here's a star, and we're looking up at the star from what? All of our singularities in G bar, and we have how many poles in that Z plane? 3, and we have how many zeros? 1. We just need to find all the angles to that star, algebraically sum them up, and find the angle of G bar of Z at star. If I ask you, what's the angle of G bar of Z at star, do you know how to get it? Now you can bring your protractor to the exam. That's fine. And we can quickly find these angles. We don't have to be precise. Oh, it looks like 30 degrees. Oh, it looks like 35. Oh, you're within 5 degrees. Fine. It's good. No, I mean, given time, you could analytically compute it. Now, here's a question. Is star on the root locus? You've already calculated the angle of G bar at star. Do you have a quick way of finding the answer to this question? All you have to do is say, is it, if the angle of G bar of Z is equal to 180 minus 180, is star on the root locus? Oh, I've scrolled away from my rules, but I hope the answer is an emphatic yes. Definitely. What if the angle of G bar was not equal to minus 180? Is star on the root locus? No. Now, here's where we get to read some bedtime stories. We're going to read the rules of the root locus. And the reason I say bedtime stories is they're kind of long. You might go to sleep, but don't. Just listen as I scroll, and we'll start to make sense of these. But we've already talked about them, actually. Here's rule number one, and I'm assuming this structure for G bar. And we started, I think, about 20 minutes late, so we'll keep going for 20 minutes. How's that? G bar of Z is N over D. Rule number one, and this one's not hard at all. Root locus branches begin on the open loop poles of G bar of Z. We've talked about that already. Those are just the roots of D of Z in that agreed generalized notation. And the root locus branches end on the open loop finite zeros of G bar. Those are the roots of N of Z equal to 0. They end there. The number of infinite zeros of G bar of Z, that's the difference between the number of finite zeros and the number of poles, and that's equal to the pole zero excess. The number of infinite zeros of G bar of Z, which equals the pole zero excess in G bar, determines the number of root locus branches that go off to infinity in the Z-plane. And we'll learn what these asymptotes are later, but we know where they are for pretty simple pole patterns, pole zero patterns. That's rule one. Just where do we start, where do we end? Rule number two, assuming that we're using K non-negative, K is greater than or equal to 0, need to watch these segments, don't we? These real line segments, these desks, we have to be careful. But the real axis segments, we have our piece of bread now. I was thinking we had a cutting board, and so I was stumbling over the cutting board. Real axis segments in the Z-plane belong to the root locus if an odd number of poles and zeros lie to the right of the line segment, and we now know why that's true. We now know why that rule exists. So the points on a root locus line segment satisfy the phase angle condition. That's where rule number two comes from. So we've drawn our X's and O's. If we have some of those on the real line, we've cut our bread, and now we've shaded those segments of the real line that belong to the root locus based on rule 2. Rule 3. This applies when more than one branch of the root locus lies on the same real axis line segment. Is that confusing? If I now have a line segment on the real axis between poles and zeros, and it's on the root locus, then I have two branches. Here I have two poles. What are they going to do? I'm going to have a breakaway point between those two poles. And it could be that I had some other behavior, some zeros, and I might have a re-entry point. Do you remember, has everybody had their Dramamine? Remember this guy? We had a breakaway point between the two poles, and we had a re-entry on the... You guys quit laughing. I'm going to start laughing myself, but we're pretty much out of time, aren't we? So we have breakaway and re-entry, but we don't always have to have a re-entry. Is that clear? Here we have a breakaway in the upper right. No re-entry. They just kept going off to infinity. So we could have breakaway without re-entry. We could have breakaway and re-entry. We still have half the lecture to go, but unfortunately we are out of time. So I will have to go home and slice some bread because I'm starving to death. But I hope you now know how to start drawing these root loci. And watch for more information. I may make some more stuff available on D2L for root locus construction.